Hello students, how are you all doing? I hope you are doing fine. Today we will do a lecture on inductance. We know what is electromagnetic induction because whenever we are having a changing magnetic field, then we have a current associated, electric current associated, and we call it as induced EMF. So that is what is electromagnetic induction. And now today we will study what this inductance is. So what is inductance? So whenever we are having any magnetic flux and this flux is changing in a coil due to another coil which is near to it or maybe in the same coil, then an electric current is induced. So whenever there is a change in the magnetic field due to one coil in presence of the other, then some electric current is induced. That is what is known as inductance. So that is what we call inductances. So whenever there is a change in the flux due to the coil itself or due to any coil which is near to it, then there is an electric current, there is an induced EMF, which we call as inductance. So the magnetic flux through any of the coil phi B is proportional to the current I which is flowing, right? Because whatever is the change in the magnetic flux, that will produce the electric current. So if you say that if the geometry of the coil does not change, the coil remains the same, then if we differentiate both with respect to time, then d phi B upon dt is proportional to di upon dt. And if there is a coil which is having capital N terms, then we can write down N phi B is proportional to I, because this is for a single turn, and if the coil is having capital N terms, then phi B will also be proportional to I. So here there is a proportionality sign, and in order to report the proportionality sign, we always use a constant, and this constant we call as inductance. So inductance depends only on the geometry of the coil and on the properties of the material of the coil of which the coil is made up of. So inductance depends on only two things. Always pay attention. The inductance is a constant. It depends on only two things. It depends only on the geometry of the coil and it depends on the intrinsic properties of materials. So as a constant, it depends only on these two things. So always remember this. And also inductance is a scalar quantity because this is a constant. It does not have any direction. So if you introduce a constant here, then this inductance is equal to phi upon I. So inductance is always flux upon current because the constant we have introduced. So inductance is flux upon current. Flux is equal to B into A and current is I. So write down the units and the unit of inductance is Henry. So we always measure inductance in the unit Henry, which is due to the name of the scientist Henry. So inductance is always measured in Henry. So there are two types of inductance which we will study just now. First one, there is an induced EMF due to the presence of another coil. So that is a mutual inductance, that due to a change in the magnetic field of the one, there is an induced current in the other. So that is a mutual effect. So we call it as a mutual. And in the second case, we are not having two coils, we are having only one coil. And due to the change in the magnetic field of this coil, the coil itself has an induced EMF. So that is self. No one else is there. Only a single coil change in the magnetic flux will create the induced EMF. So mutual when we are having two coils and one is affected by the other, and self is when we are having only one coil. So first we'll study mutual inductance and then we'll study self-inductance. So let us go to mutual inductance. So in order to understand the mutual inductance, we are taking two coils. The outer coil is in the blue color, which is having the length of small l, whose radius is R2, and this coil we are calling as S2, which is having N2 turns. And the inner coil is shown as green color, which is having the radius R1, the length is same L, and this coil we are calling as S1 and it is having N1 turns. So there are two coils in all. So these two are two long coaxial. You can see that the axis is same. So if they are having same axis, then we call as coaxial. So this is like a solenoid on a hollow cylinder. We wrap a number of turns of wire, so we call it a solenoid. So we are taking two coils in form of the solenoid. So first coil is the inner one, S1, whose radius is R1, number of turns, total turns is N1, and the number of turns per unit length is small n1. Second coil is S2, radius is R2, total number of turns is N2, and the number of turns per unit length is small n2. So these are the two coils we are taking. Now what we do, we in the coil S2 that is shown in blue color, we set the current I2. So I2 is the current which is flowing in the coil S2. So if the current is flowing in the second coil, then due to the flow of the current, there is a magnetic flux in the coil S1. And we call this flux as phi1 because the magnetic flux in the coil 1, S1, so we call it as phi1. So this magnetic flux is due to the current in coil S2. So we can say that if the flux is phi1 in the coil S1, then the total turns are N1. So we can say N1 into phi1 is proportional to I2, right? Because the flux is proportional to the induced current and the N number of turns, then N phi1 is proportional to I2. So just remember what we studied in the last lecture of the electromagnetic inductions, that what is the magnetic flux produced? It is proportional to the induced current, and if capital N is the number of turns, then N into phi b is proportional to I. So in order to remove this proportionality, we introduce a constant. So we can say N1 phi1 is equal to, because it's a mutual inductance, then we write the constant as M. And this is between two coils, so we write down 1 and 2. So the mutual inductance is the flux in one and the current in second coil, I2. This is the constant, which is the mutual inductance. And now the current I2 is flowing in the coil S2. So due to this current I2 in S2, there is a magnetic field in coil S2. So this magnetic field in coil S2 is given by B2 is equal to, this is the solenoid, and for the solenoid magnetic field B is equal to mu naught Ni. If you don't remember, just refer to my lecture, the link is given below. But for the solenoid magnetic field B is equal to mu naught Ni. So if it is in the coil S2, then B2 is equal to mu naught, number of turns per unit length is N2, and the current is I2. So B2 is equal to mu naught N2 I2. So just put the value of B2 in here, because here small n is the number of turns per unit length. So this is N upon L. L is the total length, and also phi is equal to B into A. So this equation we can write down again. So this equation we write down again as N1 phi1 is equal to N1 L pi r1 square mu naught N2 I2, because N1 is a number of total turns and N1 will be N1 upon L. So this N1 will be equal to N1 into L. So this N1 we have replaced with N1 into L, and phi is B into A. So this is B mu naught N2 I2. Why we have written? Because the magnetic field is in the second coil. That is why we have written this. And the area of first coil is pi r1 square, because r1 is the radius. So now we have two equations for N1 phi1. So now we can compare these two equations. Now we have to compare this equation with this equation. So let us see, this is N1 phi1, this is N1 phi1. This is I2 and this is I2, and whatever is remaining will become the mutual inductance. So we can write down mutual inductance M12 is equal to mu naught N1 N2 pi r1 square into L. All this quantity will become mutual inductance. So what we are doing here, we are passing the current in the blue coil, second coil S2. So there is a magnetic field in the same coil, and due to the magnetic coil there is an induced EMF which is produced in the first coil. So the magnetic flux, the change in the magnetic flux will induce a current. So this formula we have written, and on comparing we got this mutual inductance. Now what we do, we will flow the current in the coil S1. Now we will do the reverse. Now instead of this coil S2, we will flow the current in coil S1. So I1 is, so now there is no more I2, so we will strike it off, and there is now the current in the first coil I1. So this will be like the magnetic flux in the second coil due to the current in the first coil. So similarly we can write down that capital N2 is the number of turns in second coil. So this N2, phi2 is proportional to I1. Again introduce the proportionality constant M21 because now the magnetic flux is in the second coil due to first coil, the current in first coil. So M12 is the mutual inductance of solenoid S1 with respect to S2, and M21 is the mutual inductance of solenoid S2 with respect to S1. So now we can write down N2, phi2. So N2 will be written as, because this is small n is equal to capital N upon L. So capital N will be small n into L. So N2, so this will be N2 into L. And phi2 will be B into A. The magnetic field is in the first coil because the current is in the first coil. So mu naught N1 I1, the solenoid has mu naught Ni, and area is pi R. So if we compare these two equations, N2 phi2 is equal to M21 I1 and N2 phi2 is equal to N2L. This is all the formulas we have written. So if we compare these two equations, then we get the mutual inductance M21 is equal to mu naught N1 N2 pi R1 square L. So if you compare these two inductance, these are the same. So either there is a current in coil S2 and the magnetic flux in coil S1, or there is a electric current in coil S1 or antimagnetic flux in coil S2, then we get the mutual inductance as same. So from these two we can say M12 is equal to M21 is equal to M, because these both are same. So commonly we call the mutual inductance with capital M. So we have taken both the inductance as same. M12 is equal to M21 because we derived the formula and these are same. So commonly we call them as capital M, that is the mutual inductance. Now here in all the derivation we are taking mu naught because mu naught is the permeability of free space or vacuum. Now if we take the relative permeability, that means if there is some medium, then the permeability of the medium with respect to vacuum we call as relative permeability. So if the medium of relative permeability mu r is present in the solenoid, then capital M will have the formula mu r mu naught N1 N2 pi R1 square L. Only we have multiplied with mu r. So if the mutual inductance of a pair of coils, which may be solenoid or any coils, depends on their separation as well as their relative orientation. So now we can say N1 phi1 is equal to Mi2 because M is the common inductance, mutual inductance we have taken. So if the coil have the current which are varying, so we can write down if the coils have varying currents, you can write on change in current. So d by dt of N1 phi1, because we are considering the change in current, that is equal to d by dt. Differentiate both sides with respect to time. So this is Mi2. And from the formula of induced EMF, we know that the induced EMF in coil S1 is given by minus d by dt of N1 phi1. The induced EMF is due to the change in the magnetic flux of coil S1 with respect to time and in the opposite direction on combining the Faraday's law and Lenz's law. So if you compare these two equations, then you get that E1 is equal to this minus d by dt of N1 phi1. So this is minus d by dt of Mi2. So M is a constant which is a mutual inductance. So we take it outside. So M and with minus di2 upon dt. So the induced EMF in coil S1 is due to the change in the current of second coil S2. And the constant is mutual inductance. So what we can say that the induced EMF depends on rate of change of current and mutual inductance of two coils. So the induced EMF in coil 1, it depends on the rate of change of current in the coil S2, and it also depends on the mutual inductance two coils. So next what we'll move to is self-inductance. In self-inductance, we have a single isolated coil, and EMF is induced in the single isolated coil due to change of flux through the coil. And what causes a change of flux? The varying current through the same coil. So we take one coil, we pass the current through this coil, and this current is a varying current, and due to the change in current, there is a magnetic field, there is a change of flux through the coil, and due to the change of flux through the coil, there is an induced EMF in the coil itself. So like the mutual inductance, we were having two coils, we were flowing the current in one, and magnetic flux was changing in the other coil, and due to that there was induced EMF. So here we have only one coil, and in this coil we will flow some amount of current. So due to the current there is a change in the magnetic flux, and due to the change in the magnetic flux, an EMF is induced. So if there are capital N turns in this coil, then the magnetic flux of all these capital N coils is proportional to the current I which is flowing in the coil. And in order to remove this proportionality sign, we introduce a constant, and this constant we call as L. And this L is self-inductance of this coil. So L we write down as, so the constant of proportionality, which is the self-inductance of the coil. So if we vary the amount of current that is flowing in the coil, then due to the change in the current, the magnetic flux Yb also changes, and due to the change in the magnetic flux, an EMF is induced in the coil. Now we will write down the formula for EMF, that is the electromagnetic induction which causes the EMF. So this EMF is equal to change in the magnetic flux with respect to time. So this is the general formula for the induced EMF, and the equation for the magnetic flux we have written is this. So we will just put the value of N5e from this equation. So our induced EMF E is equal to minus d by dt, and from this equation N5 is equal to Li. So we write down Li, where L is a constant which is a constant of proportionality or the self-inductance of the coil. So we can take it outside the differentiation. So this will be equal to minus L di by dt. So from this equation we can say that the induced EMF within the coil is proportional to the change in the current in the coil. And here there is a negative sign, and we know this negative sign is from the Lenz's law. So this induced EMF, this is a self-induced EMF, it opposes the change of current in the coil. Because the induced EMF and the change in the current, they are in the opposite direction. There is a negative sign which shows that this EMF tries to opposes any of the change in the current in the coil. So now we know the formula for mutual inductance and we know the formula for self-inductance. So let us take an example. So if we take a solenoid, this is a solenoid. Solenoid is a hollow cylinder where we wrap a number of turns of wire on it. That is known as a solenoid. So we consider a solenoid whose cross-section area is given by capital A, and the length of the solenoid is say small l, and small n is the number of turns per unit length. So we know the formula for the magnetic field due to solenoid, because the current is flowing in all these wrapped wires. So there is a magnetic flux in the solenoid which is given by the formula P is equal to mu naught N I. I is the current flowing, small n is the number of turns per unit length, and mu naught is the permeability of free space or vacuum. So this we know from the formula of solenoid. If you want to go to the detail how we got this formula, you can refer to our lecture. The link is given below. But if there is any of the solenoid, then this formula always holds for the magnetic field. So now the magnetic flux which is associated due to the flow of the current is given by N pi B. And we know that N is the total number of turns. So the relation between the number of turns per unit length and total turns is given by, this is the total number of turns and this is the length of the solenoid. So if we divide total number of turns with the length, we will have number of turns per unit length. So we can write on capital N as small n into the length of the solenoid. Also the magnetic flux phi B is given by B into A. The magnetic flux was given with the formula B dot A. So P corresponds to the magnetic field of a solenoid. So we write it down as mu naught N I. And A is the area of cross section which is given as A. So we will write down A as simply A. We will not write down pi r square because in example radius is not given. Only what is given to us is that the cross section is A. So we will write down A as A. So we'll get N phi B is equal to mu naught N square A L I. And we got the formula N phi B is equal to Li. So N phi B is equal to L into I, where L is the self-inductance and I is the current. So these are two equations for N phi B and N phi B. So now we can compare this equation and this equation because the right hand side is same N phi B and N phi B. So if we compare these two, what we get is capital L, that is the self-inductance, is equal to mu naught N square A L. Because here is I and here is I, so this I is same. And whatever remaining here, this will become the self-inductance. If you compare these two equations, this is same, these two are same, and this should be equal to L. So our self-inductance is equal to mu naught N square AL. So if you're having a solenoid, you can use the formula for self-inductance as mu naught N square AL. And if inside of the solenoid we put any of the material, any of the magnetic material whose relative permeability is mu R. And the relative permeability mu R is given by the permeability of the material divided with the permeability of free space. So if we are having any material here whose permeability is mu, so mu is given with the value mu R into mu naught. So instead of mu naught, we will have mu here. So our formula for self-inductance will become, now we are not having mu naught, we are not having free space, we are having any magnetic material of mu. So instead of mu naught, we have to write down mu, and mu is mu R into mu naught. So mu R, mu naught, N square AL. So if there is free space within the solenoid, there is vacuum within the solenoid, then we have to use this formula. And if we will any of the magnetic material with permeability mu, then we have to use this formula. So from here what we see that this depends on material only. Small is the number of turns per unit length. So this will remain the same. If you increase the length or decrease the length, it depends only the number of turns per unit length is the cross section and small as is the length of the solenoid. So we see that self-inductance depends only on the geometry of the solenoid or the material of the solenoid. And it also depends on the permeability, that means ultimately the material of the solenoid plus the geometry of the solenoid. So from here we can see that this EMF is working against the change in the magnetic current or the production of magnetic flux. So this EMF is working. So if there is current is establishing, that means we have to work against EMF. So now we have to calculate the work done against EMF in establishing the current. How we can calculate that work? So if we want to establish the current I at any instant in a circuit, then the rate of work done. So to establish the current I, so the rate of work done is given with the EMF into the current I. And the EMF is given by the formula for the self-inductance as L di by dt. Here we are writing only the magnitude of the EMF because minus shows a direction that this EMF has to work against the change in the current. So minus we are neglecting here, we are taking only the magnitude. So just put the magnitude because here we have a magnitude of EMF. So just put the value of magnitude. So the rate of work done is given by dW by dt is equal to L I di by dt. So this is the rate of the work done. Now if you want to calculate the total amount of work done in establishing the current I, then the total work done which is used to establish the current I is given by, so if we integrate this, the rate of work done, then we will have the total work done. So it is dW, that means we have to integrate this LI/dI. This is the rate of the work done with respect to time. So if we want to calculate the total work, then we have to integrate the small amount of work, and the small amount of work is given by LI/dI. So you see here L is a constant and only I is varying. So I is varying, initially the current is 0, then we have to take it to the value I. So the integration limits will start from 0 to capital I. Initially there is no current, current is 0, and finally we want to establish the current I, capital I. So the limit goes from 0 to I, and the value is LI/dI. Now integrate this, you will have the total work done. W is equal to, L is outside, it is a constant, and I/dI will be I squared by 2. This is the integration of I/dI. So that means the work done which is needed to establish the current is half Li square. So this amount of the work done is required to build up the current capital I. One more thing we want to calculate, that if we have two coils which are nearby, so we can see that there are two coils nearby. So here you can see two coils and the current is flowing in both the coils. So the flux linked with one coil is the sum of two flux. Suppose the current I1 is flowing in this coil and I2 is flowing in this coil. Then due to this current there will be a magnetic flux in the coil 2, and due to the current flowing in coil 2 there will be a magnetic flux in coil 1. That is due to the mutual effect. But if the current I1 is flowing in this coil, then it will also be having some magnetic flux due to the varying current. Similarly, our coil 2 will also be having some magnetic flux due to the varying current. So say for example, if I take this blue coil, then this blue coil will have magnetic flux due to the change in current of the coil itself and due to the change in current of coil 2. So for any of the coil, the magnetic flux will be the sum of two coils. So we can write down, say this is our coil 1, the number of turns is n. So due to in coil 1, the magnetic flux will be the sum of mutual inductance of 1 to 1, which we can also call as self-inductance, but here for reference I am taking mutual inductance due to the current in 1 and which is in coil 1 due to coil 1 itself. So M11 I1 plus M12 I2. This is the mutual inductance due to coil 2 and this is the mutual inductance due to coil 1 itself. You can also call it as self-inductance. Now as we know that the induced EMF is proportional to the change in magnetic flux with respect to time, and this is the induced EMF in 1, so we can write down as E1. So we get that E1 is equal to, now we are having the value of N151, so we have to differentiate this equation with respect to time. So this is equal to minus, now put the value of N151 from this equation. So this is equal to minus M11 di1 upon dt plus M12 di2 upon dt, and this M1 is mutual inductance in the one coil due to itself, so we can also write it as self-inductance. So our induced EMF in first coil is equal to minus L1 di1 upon dt plus, now so our induced EMF is equal to minus L1 di1 upon dt minus M12 di2 upon dt. So if you are having two nearby coils and you are asked to calculate the induced EMF, then you have to take into account the self-inductance as well as the mutual inductance for both of the coil. This we have done for coil 1. Similarly, if you want to calculate the EMF for coil 2, then similarly you can write down this will be the sum of the self-inductance of the coil plus, because it is with a negative sign, so it will be So whenever you are having two nearby coils, you have to take into account the self-inductance as well as the mutual inductance, and provided that current is flowing in both the coils. So always keep it in mind. Remember this always. Now we'll quickly do one application of electromagnetic induction that we use in our households, and that is a generator we call in common language, and it is an alternating current generator, that is an AC generator. So let us see how an AC generator works on the principle of electromagnetic induction. So as an application of electromagnetic induction, we are starting AC generator. So for this AC generator, we take a coil. This coil we have shown in blue color, and this coil is capped between two permanent magnets. Here you can see this is the north pole and this is the south pole, which is shown in this side. The other side, this may be S and this may be N. So this coil is capped between two permanent magnets, and it is capped such that it can rotate. So this coil is capped on a rotatory shaft. That means we can rotate this coil with 360-degree angle within the magnetic field created by these two permanent magnets. And the axis of rotation of coil is perpendicular to the direction of magnetic field. So this coil is mechanically rotated in a uniform magnetic field by external means. So we are using permanent magnets and we are doing some mechanical work to rotate this coil within this permanent magnetic field. And if we are rotating this coil, then due to the rotation, the magnetic flux through the coil will change and induced EMF is produced in the coil. This coil is connected to the external circuit, as you can see here. Here we have some external circuit. So there are slip rings and there are carbon brushes. So this coil is generally called with armature. So this coil and armature, do not get confused with the word, because coil and armature are one and the same thing. So we are now done with the construction. Now let us see how it works. So we rotate this coil with a constant angular speed omega. Let us say omega is the angular speed of the rotation of the coil. And if the angle is theta, then theta is equal to omega. That is the very famous relation in physics. We already know that if omega is the angular speed, then the angle theta is given by omega t. Here theta is the angle between the magnetic field at any instant. So now we can write down the magnetic flux phi b. Phi b is given by b dot a. So this dot product gives us BA cos theta, and theta we have already written as omega t, so this is equal to BA cos omega t. Now just pay attention here, because phi b is equal to BA, had the angle been 0 degree, they are in the same field, they are in the same plane, then we have written as simply BA, but this axis is rotating. So this is the magnetic field and this is the area. So area, we can take the axis as a coil, you can write down, or you can write down as this area. So this theta is varying, so we can write down the magnetic flux phi b is equal to BA cos omega t. Now we have to write down the electromagnetic induction, so we can use Faraday law. The EMF is given with the change in the magnetic flux. So if there are n terms, then E is equal to minus n d phi b upon dt. Now we have to differentiate this phi b with respect to time. So we get the induced EMF E is equal to minus n, and this is d by dt. So cos omega t will give us sin omega t. So this is BA omega sin omega t with a negative sign. So we get the induced EMF is equal to and BA omega sin omega t. So what is the trick to remember for a AC generator? The only thing is that in AC generator we have a coil and we keep it between the permanent magnets, and this coil is rotating at 360 degree. Because it is given a rotation, so we have to write down the angular velocity omega, and theta is equal to omega t. Then write on the flux, then write on the Faraday's law. So we get the equation as NBA omega sin omega t. Remember, there is a rotational motion. So rotational motion, then omega is always there. So whenever you get AC generator, keep in your mind that omega is there. So whenever there is omega, the formula always is NB omega sin omega t. And if you want to learn more simple way, then you can write down E is equal to E naught sine omega t. You can also remember this way, E is equal to E naught sine omega t, where E naught is given by NBA omega. So this is the EMF induced or the current which is generated. So when this EMF will be maximum, it will be extremum. So this omega t corresponds here to theta. So omega t is equal to theta. So we'll have the maximum value of sine theta for sine 90 degree. So whenever our theta is equal to 90 degree, then we'll have the maximum value of EMFE. Also, if it is 180 degree plus 90 degree, that means when our theta is equal to 270 degree. So again, we will have maximum EF. So we'll have our EMF extremum or the maximum at these two values. So how to find out the maximum values? Whenever you are having any trigonometric function, either it is a sine theta or cos theta, and you have to find the maximum or minimum, just pay attention to this value sine. So sine theta, that means sine theta will be having the value maximum of +1. Where does +1 value exist at? Either 90 degree. So our EMF is extremum or maximum at only 90 degree, or it may be minimum when we are having the sine theta is -1, then we're having the minimum value of it. Now what we are getting here, we are getting the EMF, and that is an alternating EMF. So we can write down our angular frequency as 2 pi nu. Omega is equal to 2 pi nu. So this equation may also be written as E is equal to E naught sine 2 pi nu into T. Because omega we have replaced with 2 pi nu. So this all is angle. So in this equation we can say that this all is angle. So we can write this down that this will be theta. So the value of sine theta will be maximum for +1 and minimum as -1. So whenever we are having the maximum value, then this whole sign will be +1. So we will have E is equal to E naught. And when we'll be having minimum, then this sine theta will be -1. So the minimum value of EMF is minus E naught. So here you can see that it is varying from positive to negative value with the equal magnitude. So we call it as alternating EMF because our EMF is varying from plus E naught to minus E naught. So after looking at the AC generator, we can make certain conclusions. What are those conclusions? Say, for example, if I want to say that this is the direction of magnetic field, it is the direction of magnetic flux, so it shows the direction of magnetic field. So our B is along this direction, this we are showing the direction of magnetic field. So this is the direction of field B. And say our coil is at 90 degree. If we rotate it such that this angle is 90 degrees, so then you can say that the angle between the magnetic field and the area of the coil, first step we can see is whenever armature is 90 degree to magnetic field. So whenever armature is 90 degree to magnetic field, that means our magnetic field and the area vector are along the same direction. So that means that angle between them is 0 degree. So these two are parallel to each other. Angle is 0. So our induced EMF, that means the magnetic field and the air field vector are parallel to each other. And if these are parallel to each other, that means the theta is equal to 0 degree. And we have our induced EMF E is equal to 0 because E is equal to E naught sine theta, where theta is equal to omega t, or you can write down as theta is equal to 2 pi nu into t. In this case, our E is equal to 0. When we rotate it within 190 degree, then it is parallel to magnetic field. Our armature is parallel to magnetic field. And if our armature is parallel to magnetic field, that means our magnetic field and the area vector are perpendicular. And if these are perpendicular, then E is equal to E naught, because theta is equal to 90 degree and sine 90 will give us 1. So E is equal to E naught. When we rotate the armature with more 90 degree, so that means now we have rotated it up 180 degree more. So again it gets 90 degree to magnetic field. So when it gets 90 degree to magnetic field, that means our B and A are again parallel. And if B and A are parallel, that means our induced EMF is again 0. And in the fourth stage, so this is up to a 270 degree rotation. Up to 180 degree rotation. Now we rotate it more with 270 degree. Then our armature is parallel to magnetic field. So when it's parallel to magnetic field, again after rotation, that means our magnetic field and the area vector are anti-parallel. And if these are anti-parallel, are perpendicular. These are perpendicular but in the opposite direction. So we have E is equal to minus E naught. And again when we rotate the armature with 360 degree, then again it is 90 degree to magnetic field. And when it is 90 degree to magnetic field, that means our magnetic field and area vector are parallel. These are parallel, then again our electromagnetic induction, your EMF reduces to 0. So if you plot this on a graph with respect to time, then what you will get it as? That in a complete rotation, it is at 0, now it is T by 4, and then it is T by 2, then it's 3T by 4, and this is one complete time period T. So initially when it is 90 degree to the magnetic field, that means B and A are parallel and E is equal to 0. Then at T by 4, B and E are perpendicular, so it reaches to the maximum value of E naught. Then it again becomes 0 at T by 2. Then at 3T by 4, it again reaches to the negative value, and at T it is again 0. So here when our armature is 90 degree to magnetic field, then B and A are parallel, and here the value EMF is 0, and here at T by 4, when it is parallel to the magnetic field, then B and A are perpendicular, then E is having the maximum value as E is equal to E naught. Again when we rotate it 90 degree more, then our armature is 90 degree to magnetic field and B and A are parallel, and we have E is equal to 0. We rotate it 90 degree more, that means we have rotated with 270 degree total. So when it is rotated with 270 degree, then B and A are again perpendicular. But if you put the value of sine 270 degree, then it is minus 1. So we will have E is equal to minus E naught. And again, if you rotate it one more 90 degree, that means 270 plus 90 is 360 degrees. So that is a complete rotation. So after a complete rotation, again, the magnetic field and the area field vector are parallel, and we get E as 0. So this is the way we rotate the armature of a AC generator coil, and we generate the alternating current whose values goes from plus E naught to minus E naught. And we rotate this armature, we need some mechanical energy. So there are different types of, first type you can write down as hydroelectric generators, and hydro means water. So whenever you are using these generators to generate the induced EMF or to generate the AC current, then we use a water falling from a height. Like for the dam we use The hydroelectric power we use to rotate the armature. Or we can use a water steam at high pressure for the rotation of armature. And if you are rotating the armature using the water steam, then it is called as a thermal generator. And other times we use some nuclear fuel. So if you are using a nuclear fuel to rotate the armature of a AC generator, then it is known as a nuclear power generator. But it is not generating the nuclear power, it is using the nuclear power to generate the alternating current. So these are the three types of generator which are most commonly known. So you should always remember hydro means water. So we are using water from the dam to generate the AC current. Thermal is when you are using the water in form of steam. That means you are using the thermal properties of water to generate, and either you are using a nuclear power or nuclear fuel to generate AC current by rotating the shaft. So these three types are most common, and you have seen how we generate the AC current using an AC generator. So this is a most common example of how we use the induced EMF in our practical applications. So that's all for today. Stay connected and keep on watching the lectures. Like and share. Please comment in the comment box and subscribe to our channel so that you can continuously receive notifications for more such interesting lectures. Till then, keep learning, keep safe. Thank you.